That's not the Hello everyone. Um, so today is our third lecture on machine learning and tutorial. So yeah, you were able to understand the previous one, that maximum likelihood and close.
So, excuse me.
Yes.
The class will be based on week 2 or week 3 today's
Uh,
session. It
uh,
will be based on which week?
week 3 only.
Okay, okay. Thank you.
Yes. Week 3.
Sir, one question. In week two, only 9 questions are there, sir, in assignment, and like whatever the result we got is calculated as per questions, 10 questions, sir, which is wrong, sir.
Only 9 questions are there.
Yes, sir.
Let's see. This is the one, right? 9 questions are there. Results for 10. Don't worry then. Means like for everybody it is that. So will not matter that much.
No, sir, but the percentage is less, sir. If our wrong, then the total percentage should be 90%, but it is showing 79.
Oh, then I'll have to see. But you are able to understand that maximum likelihood estimate and bias variance. Able to understand this one? These things you're able to understand. Hello.
Hello, sir.
Yes.
Sir, can you please take the likelihood from the starting itself because it's a critical one, I think. So can you precisely take it?
Okay. What we did was like we likelihood is the probability distribution. Distribution that is a joint distribution. The distribution of that the TI that I defined here as the Y values. Okay. Means like the from means the dependent one. Okay. And so distribution of that with respect to the parameters w and beta, and x is the independent variable. Okay. And that is defined for means so for each training examples this is the one. For n training examples, multiplication over n. Okay. And for engineering problems we usually consider the likelihood to be normal distribution. Okay. And here according to our definition the mean is going to be w transpose phi x, and the variance is going to be a variance of this error, that is beta inverse. Okay. And so like week 2 done. So any other problem other than this? Bias variance you understood? Okay. um this we have to, as you can understand, the likelihood of our model predicting our data points ti is what we have here. So it will be a curve that like goes almost through all the points. Okay. So for that we have to maximize the likelihood. Okay. And for that, and we have to get the parameters with respect to that. Okay. Parameters here are w and beta. So so first we take log of that, because log is an increasing function, so it does not change the nature of the curve, is nature of the critical points. Okay. And like taking log and separating the variables. Okay. With respect to beta to get the value of the beta, and then after that with respect to w. Okay. Any problem up to this? Hello, able to hear? Hello. Understood up to this?
Yes, you're audible.
Yes.
You started just now. Means you're on slide number 10 now.
Means I'm doing the previous one actually. Previous
Okay, okay, okay,
maximum likelihood.
okay.
You understood this one? Maximum likelihood. Means
Yes, yes.
maximizing the likelihood to get to our cost function. Okay. So as you can see, first we take log of the likelihood. Then for maximizing, we have two parameters beta and w. Beta is a scalar one, okay, and w is a vector here, okay. So with respect to these, get the we have to means maximize the likelihood, okay. So here as you can see, differentiating with respect to beta and putting that equals to 0, we get the value of the beta to maximize the likelihood, and here for w, hmm, for w, here also we differentiate and we get this expression, okay. And maybe after that we had problem while vectorizing, right? So so the idea was that like um so like ti are the y values, right? So that the dependent values, and so for vectorizing I make a vector t comprising of the ti values, okay. And I define the phi, okay. The here phi was like that phi means phi was like this, okay. This x1 square, then x1 x2 square, and sine this like means can be anything x1 x2 like that combination, okay. So vector of this, okay. So what I mean is like x1 square and x1 x2, so vector of that, okay. Okay, like this a vector, okay. So phi was a vector here, okay. Now when we are writing this equation, phi is now a matrix such that each row is our vector corresponding to one training example, okay. And likewise we have n rows, okay. Phi is defined like that, n rows of training examples, and this will be p plus 1. P is the number of variables and 1 for the bias term, okay. So p plus 1 here, okay. So p it is n cross p plus 1. Phi is defined like this, okay. So if you have tried yourself, you can like see that this can be defined like this, okay. Okay, and what I have done after this is like take means flip the equation first, okay. So this comes means the see the right as the left, okay, and then I have taken the transpose of that to get to this one, okay. I multiplied both sides with phi transpose phi inverse to get this equation. This is the name of this is actually called Moore Penrose or normal equation. Okay, but as you can understand, like if our data is low or our parameters are means lot many parameters, lot of this x terms we have, then this can, or maybe this can overfit. Okay, okay, so and okay, okay, after that one more thing actually. If not, so is actually Andrew Ng, machine learning expert. His notes, let me share. Does it work? It does work. Okay. So this is Andrew Ng's notes here. So you can see this derivation. Uh, so I was telling, yes. So he has derived it like both ways. Means what I have done is I have done this probabilistic derivation here. Okay. As you can see, this is the likelihood function he has derived, and okay, and after that maximizing the likelihood to get to the square error. Okay, and if you take the differentiation of the squared error, then you can get to the this normal equation. So what he has done is done it another way as well. So first he has done made the matrices and vectors. Okay, and after that he has taken this gradient of this cost function. Cost function is defined like this. Okay, okay, so both ways actually. So read this. Okay, okay, actually I got this slide from one of our professor at IIT Delhi. Okay, he teaches machine learning, and this one actually, linear regression. Okay, this slide, there's this talk about from it. Okay, so from there you can get it. So so the both ways to derive that. Okay, just revisiting bias variance for once to get to our next topic. So as you can understand, with the maximum likelihood we can get to an overfit condition like this, which has high variance and low bias. Okay, but then it will not generalize well, and it will do poorly on the test data, as I've shown here. This green crosses are the test data, so it will to do bad on that. For that, as you can see, uh, yeah. So our first method to address high variance and low bias situation is regularization. Okay. So next we are going to study today is regularization. Okay. So the slides are from, this picture is from Andrew Ng again. His that machine learning course Coursera. So so this is the high bias variance one. Okay. So our problem is this one. Using maximum likelihood estimator and the squared error function, we will get reach to this problem. Okay, it is so well fit that it cannot generalize over new training example. Okay, so there are two types of regularization: L2 regularization and L1. Okay, so the thing is like L2 and L1 both are like used in every problem actually. Regression, logistic regression, or linear regression, neural networks, everywhere actually. So the idea is to just like given a cost function, this is for a linear regression squared error cost function, just add this term. Okay, I have defined the w as the parameters, right? Okay, so this is the parameter, scaling parameter it is called. Okay, so lambda times summation over this wi square. Okay, so the idea, this is another slide, screenshot from the video. So the idea is like this: if you means like he has defined like this to be the best fit. Okay, but suppose we take means I don't know what is going to be best fit, so I take two more variables, x3 cube and x4 cube. Okay, so you can understand that this x means that x and x square are going to remain small, but as you increase the power here, the means um, the coefficient of theta 3 can become really big. Okay, theta 4 as well, so they can overpower the total uh, that curve we have. Okay, so what he has told that you understand, if we add two terms which are huge. Okay, so what will happen to make this work means, to make, suppose this is a total cost function. Okay, so cost function or loss function. So if we make it too large, and then the theta 3 and theta 4 have to be very small to minimize this function. Okay, so this is the idea actually. Okay, that theta 3 and theta 4 will become very small if we add some extra values here. Okay, if we add this value, this so he has defined as theta, we are doing with w here. So this w, few w's will be very small. Okay, close to zero. Some suppose like in this case, this x and x squares are important. Okay, so they will not be reduced here. Okay, or maybe very less reduced, as you can understand that. And here, as you can see, the theta 0 is always important, so it will not be reduced at all. Okay, okay, so so any doubt like up to this? No doubt, right? So what we do is like, okay, as you can see, close to zero, some of the parameters. Okay, not all. Okay, let me write it down. So when this is applied to linear regression problem, it is called a ridged regression. Okay, and so next we are going to get to the derivation of this. Okay, so we derive this ridged regression using like ML, you have read. Okay, so this is called MAP. Okay, so this is maximum a posteriori estimate. So the idea is like to show you. Uh, Idea is from Bayes theorem actually. Mm, let's see. Mm, well, I cannot find that slide now, but but Okay, let's learn from Wikipedia. So Bayes theorem, and the important thing is like as I have previously said as well, the probability part is very important actually. Okay, so as I said, doing, keep studying. Uh, where is his courses? This is the one. So keep doing this lectures as well. Okay, all these lectures are important. Okay, okay. So you'll have good background to understand this. Okay, and what I was telling. Okay, Bayes theorem, right? Okay, so as you can see here, um, where posterior is defined as the posterior distribution that I'm telling about, likelihood times prior divided by evidence. Okay, so this is PA is called the prior. Okay, PB given A is called the likelihood, which we have seen. Okay, and this PB is called the evidence or total probability. Okay, so idea is like this. Doubts, let's see. Link of probability theory in NPTEL. Okay, let me share. Uh, this is the one. No? Do every lecture of that. Okay, and solve the problems as well. Important, very important. Okay, but for upper knowledge, this is the Wikipedia page. Okay, so this is called the prior probability. Okay, and okay, so what we are doing is, what we will be doing here. So we will like we had the likelihood. If we multiply it with the prior, okay, then what happens is, okay, so you see here, this expression is called the posterior. Let me write it down. Okay, so to understand, what we needed was like probability of the parameters when this means the distribution of the parameters, like okay, means PDF. Okay, PDF, probability distribution function of the parameters W when this TPX are given. Okay, so what I have defined is like you have seen in previous, this is the likelihood. Okay, so this is the likelihood, and this PW, that is the distribution we have defined of the parameters. Okay, and multiplied that with the likelihood to get the posterior. Okay, now not to get the posterior, but this is proportional, this multiplication is proportional, means the posterior is proportional to the to this multiplication. Okay, let me show you. So as you can see, for to get the posterior we need to divide it by the evidence PB. Okay, we are not doing that. Okay, what we are doing is we're just multiplying this. Okay, so this is proportional, means the posterior is proportional to this product. Okay, but not equal. Okay, any doubt up to this? No doubt. Okay, so the thing is like, the idea is that in using this, we can get to the a regularized, more robust linear regression which does not overfit. Okay, on a higher dimension of parameters. Okay, so let me explain it how. Okay, so as you can see here, this uh, this dotted line is our normal density. Okay, and which means that, which means that, mm, this means like, means the normal distribution. Okay, so as you can see, as the value of the parameters increase, means the absolute value of the parameters increases. Okay, what happens that, then their probability of occurrence, okay, reduces. Okay, as you can see, the probability density reduces. Okay, so the idea is that, means if the values, means higher values becomes large. Okay, we are going to make them close to zero, means they are as good as not occurring. Okay, so that is the idea actually. So likelihood times prior times likelihood. Okay, posterior is proportional to prior times likelihood. So to get to the L2 regularized form, we need a prior of Gaussian. This is the Gaussian distribution of these parameters W having mean equals to 0 and variance, means, as you can understand, this is like a vector. Okay, of sigma, sigma 0 square. Okay, so means like this is multi-dimensional Gaussian. Okay, and the variance in each direction is sigma 0 square. Okay, equal. So that is what we have considered. Okay, so but idea is also like this, like, prior, what it means, like what prior belief we have about this W parameter. Okay, so as you can see, we are considering it to be normally distributed. Okay, become, which means that if the W values are small, they are more likely to occur. Okay, so that is our prior belief about W. So this next three slides, as I was short of time, I took it from another professor at IIT Delhi. So the idea is very similar to, as you can see, prior times likelihood. Okay, and after that we take log of that. Okay, it's the same thing that we have done. Okay, so as you can understood, as I have earlier shown as well, that for as these are IITs. Okay, so they are their distribution is independent of each other, so we can divide it, means we can separate each of the distribution product of that. We have taken a log of that. Okay, like previously we also took the log. So both likelihood part we have done before, so maybe you can focus on the prior part. Okay, so after that, as you can understand, log of a product becomes sum. Okay, so sum, and after that only separating the variables, the dependent terms. Okay, so as you can see, the wi terms are only we are interested in. Okay, that is the second term. Okay, and the last term. Okay, so you can understand, you can see that we have reached to that regularized form of the cost function. Hmm. And okay, so this is the regularized form, and okay, and solving like before, we can get to this closed form solution as well, in which this parameter lambda of the regularization, as you have defined here lambda, okay, lambda will come here as like this, okay, and this is the closed form of the means for getting to the closed form, you need to take difference. You need, sorry, you need to differentiate with respect to w, okay, and you will reach here, okay, like previously we have done. Only previously you can see this lambda I term was not there, okay. So what happens is, like, you get a better fit to the data, means not a overfit, and so that hypothesis will also be able to predict well for the new data, that is, it will be able to generalize better. So next, L1 regularization means in which we use a uh, this one, okay, that is as you can understand, what do you say, L1 norm here, okay. So just I'll explain the norm as well. So as you can see here, mm, hmm, so that the distance one that we have talked before, it is same as that, okay. So for p equals to 2, we get the Euclidean norm, that is the L2, okay, L2 norm, okay, as you can see LP space, maybe here something, okay, that one is enough actually. So and if for p equals to 1, we get the for p equals to 1, you'll get this L1 norm, okay, that will be the mod of this, okay, lambda times mod of wi, okay. So so this is if applied to regression problem, it is called lasso regression, and it actually puts the higher dimension terms parameters of the higher dimension term exactly 0, okay. So that's the benefit of, so means like, what you can understand it like, it is like better in the sense that means your cost function will simplify a lot. If the terms that are not required, it just removes those terms. In a L2, you'll not be able to remove the term. They will always remain as small terms, okay. Okay, so for this derivation, what we do here is use the Laplace distribution, okay. So here previously we used the normal distribution for the prior, so in this case we have to use the Laplace distribution. So let me show you. Okay, so this is the expression of the Laplace distribution. So you can consider the x to be w here, okay, and as it should be centered at 0, okay. So mu equals to 0, Okay, so as you can see from this curve, okay, uh, as you can see, this Laplace distribution means like is like very much close to zero towards the end, okay, when the W value is high, but it shoots very quickly to highest value as we come close to zero. Okay, so as you can understand, this is a much powerful regularizer. Okay, so this is actually better, but okay, I will tell it later. Okay, you can understand this for mu, different values of mu's and different values of b, the distribution how it is spread. Okay, so what we have to do is now means use w in place of x, okay, and put mu is equals to 0, and just do the same derivation. You will get your this one L1 regularized form, and after that closed form solution. Okay, what does closed form mean here? Anybody can tell me? Everybody can hear me? What is closed form? No. Okay. So, so the closed form is the solution, as you can derive it twice here. Okay. So it is like the exact solution of the W. Okay. Means like means using one formula you have calculated the value of W, and the we have another iterative approach very popular, that is called gradient descent. Okay, gradient descent is an iterative approach, okay, where we slowly come towards the solution, that is W, but we actually never reach to it. So that is not the perfect solution. Okay, okay, but this is the perfect solution. So that is called closed form. Okay, so what happens is this is more robust. Okay, means like as it simplifies the hypothesis, and also you can understand that it it is another thing is which is not in this. Okay, this using the Laplace distribution, you can get to a regression in which if there are like outliers, suppose it can happen that erroneous uh, measurement we have taken, suppose a point is here. Okay, so using the Laplace distribution you can means it will work very well if you take the Laplace distribution as the prior. Okay, means like it will almost ignore this point. Okay, okay, so this is it helps in creating robust regression. Okay, so means the outliers don't have much influence here. As you can see, one post I found at Stack Exchange, stats.stack exchange. So as you can understand, while the normal distribution is more diffuse around zero, so non-zero values have greater probability mass. Other, okay, but the Laplace one peak around has a peak around zero. Okay, okay, so means like it is means if the values are small, it almost does not do anything. Okay, but if the values are large, it quickly makes them zero. And other such distributions which help in these robust regressions are Cauchy or T distributions. Okay, student teach distribution, which maybe you'll learn in the probability course. Of course, I'll not go there. Okay. And you can see different ways. Okay, MAPs here explained. Okay. Okay. Um, Next we are so up to this, any doubt? Any doubt up to this? Hello.
Sir, can you please solve numericals so that it will be easy to understand these concepts?
Means like this is what is like means like this is you cannot find numericals here. Means in the regularization means there was there, I think, in the uh, not numerical but some MCQ, I think in week 2 there was. Oh, not this one, it's the old one actually. Okay, quiz 2, but this is a mostly a theoretical concept. Okay, ridge regression. Ridge regression was there, I think. Not. Oh yeah. Okay. So so what it helps is like means like the question is like you can understand. Machine learning is not for solving like small problems, MCQ problems, uh, or like a math problem doing pen and paper like that. So what you do is you code it out, okay, and you get the solution, okay. So as you can understand, our problem is that we are overfitting and we need to get to a better fit, okay. And so this regularization comes into hand, okay. And the thing is like if we, well, this is the closed form as you can understand, but there is also a method called gradient descent, okay, to get to our minima. And interesting thing is like in gradient descent, uh, what is it? Yes. So this is the cost function with L1 regularization, and this is the cost function with L2 regularization. So you can understand in regularization means in gradient descent, we have to take the derivative of the cost function, okay, and subtract it iteratively to get to our minima from the parameters we have. I means I'm just telling it lightly now. Okay, so you can see that in L2 regularization, as it is square, we can easily take a derivative. Okay, but in L1, as this is a mod, okay, so we cannot take a derivative. Okay, as at as you can see at wi equals to 0, this is non-differentiable. Okay, so we cannot take a derivative. Okay, and you must understand that this gradient descent is more popular than this closed form solution. Okay, so that is why L1 regularization is usually unpopular. Okay, though it works better, but it is unpopular because of difficulty with derivative. So as I was telling, means like it is machine learning is not for solving small problems. It is like you're given a data and you have to find pattern in the data. You have to code it out, okay. And those things we have not done till now. So there you will find the importance of this actually. Okay, so had one problem here as well. Where was this? Okay. Yes, as you can see. So ridge has sparsity constant, it will drive coefficients with low values to 0. That is wrong. Okay, it cannot get it to the 0. For sparse regression, you need lasso regression. Okay, L1. Okay.
Sir, please explain sparsity.
Yes, the sparsity is that means like as I said in L1 regularization, as it reduces every parameter to means every undesirable parameter to 0. So the our hypothesis becomes simpler and smaller. So that is called sparsity. Okay.
Okay, sir.
Okay. So this is the one problem here. More like practical. This concepts are more important when you implement the algorithms, not while solving problems. Okay. And so we next move to the linear classifier. Okay. And actually I was in.
Sir, please explain other statements too.
Acha, let's see. Doubts. Assignment 3. Yes. Actually, what happened is like I was little lack of time. Okay. So I have not been able to prepare the slides very um, a lot of the slides. Okay. So maybe I'll be able to cover less today. So but a few problems I'll be able to solve from assignment 3, but not all today. Okay. And so what I was telling. Okay. Other statements here, right? Yeah. So as you can see, uh, means these are not exactly correct actually. Which does not reduce the number of variables. It makes them close to 0, but not exactly 0. Number of variables. You say that actually. So this is wrong. Second point. As you can see, the ridge has also closed form solution, as you derived as well. Okay, there. And okay, means it may reduce also. It is called may actually. Means it may not be very close to 0. Okay, so reducing the number of variables is not correct when it comes to ridge regression. Lasso is better in that. Okay, if there are two or more highly collinear variables, okay, lasso will select one of them randomly. Don't know about this actually, honestly. Highly collinear variables, one of them randomly. Not sure about the last part actually. We will clarify in next class. Okay. Uh, okay. So let's move to the classification problems. Okay. So our linear classifier. So the idea is that uh, here suppose our previous problem is that, okay, and we have to separate to these two, okay. Okay, so it will be a straight line, okay, separating these two planes, okay. And so this is our classifier, okay. And okay, so this is it. And next what we get into is okay, so question number fourth fourth is actually solved from this one, okay. Previous class I have derived. Fourth you can get from here, okay. Just use this expression, okay. And okay, you can use this one, or in the first lecture that I have explained, you can means like separately differentiate it, okay, to get to the answer. Have you attended the previous ones, previous lectures, Sandhya? No, sir. Then you can check the recordings actually. Otherwise, explaining this all again. Okay. And so where we were here. So as you can understand, we here need a classifier. Okay. So what happens is that we need to give whether this is a tumor or not. Okay. Means if a person has a tumor, the person has a cancer or not. So 1 or 0, okay. So as you can understand, at okay, let's see, uh, need a to draw, okay. So okay, so what we have done here means like in this one, as you can see, uh, in this case, this is a like two parameters are there, so it is not easier to solve. Here I have taken only one parameter, that is the size of the tumor, okay. And you can understand it like what we need is, suppose this size x0 is there, okay. Above x0 it gives 1, means that there is cancer, okay. And below x0 there is no cancer, okay. So that is our uh, can you go through and solve related examples to solve the problem? Yes, going towards that only. Just wait a minute. So so this is our condition of that classification, okay. That if the tumor size is greater than x0 we get 1, if it is less than 0, okay. But what you can understand it like this. So what we get here is, suppose our hypothesis is there, h, our classifier is a theta 0 plus theta 1 x, okay. X is the size of the tumor, okay. And okay, and you can understand it like when this value uh, is greater than equals to, no, 1 minute. So so we define the nonlinearity is like you have this classifier. We put a we put a function g, okay, and which denotes that which means like, as you can see in our linear regression case, we had this only linear combination, but in this classification problem, we put an additional g, which gets which is a non means a function to introduce non-linearity in the problem to get our hypothesis. Okay, so that is our definition for now. Okay, so what I have told here is so this is the line. Okay, so as you can see, I have made a vertical line, but it can be tilted like this as well. So this is the our classifier. Okay, like in this case, it was the classifier. Okay, so the idea is that above a specific threshold x0, we get this. Okay, and the problem is that as I said, our most popular algorithm here uh, is most popular algorithm of optimization is gradient descent. Okay, and gradient descent, you need to take differentiation, but here this differentiation is not possible. Okay, so what we do is we take a non-linear function g that I've said. It is called sigmoid. Okay, sigmoid function. Okay, so as you can see, this is 0 and this is 1. Okay, so this is the 1. Okay, so idea is like this. Okay, if uh, if the value and if the value is 0 here, okay, x value is 0, you get 0.5 in sigmoid. Okay, so okay, so the function equation is 1 plus e to the power h theta x. Okay, so this is the sigmoid function. Okay, means like okay, just wait a minute. This is not the sigmoid function, means like, so for this let me write it clearly. So this is fx. So this is the sigmoid function. Okay, fx is equals to 1 upon 1 plus e to the power minus x. Okay, so in place of x, we put the linear, means linear combination of theta 0 and x into this. Okay, so this becomes the uh, hypothesis. Okay, so I mean to see, I'll write it down. Next slide. So yeah, so what I mean to say is this hypothesis I have defined as yeah, hypothesis I have defined as 1 upon, as you can see, it's like I put the theta 0 plus theta 1 x into, actually everyone is able to see the slides. Is it not too small? Okay, I think so. So what I define it as theta 0 plus theta 1 x. Okay, so you can see here, what I mean to say is, if theta 0 plus theta 1 x means, uh, if the x value increases, so what will happen is, as the x value increase, so this whole term will increase. Okay, so we're moving towards this direction. As we get to higher value, we'll get 1. So we have a tumor case. If the x value reduces, okay, means this not x value reduces, then we get towards 0. Okay, so there is no tumor. Okay, so the benefit of the this sigmoid function is that it is differentiable, and and we can use it for gradient descent. Okay, and okay, okay, so what more do we need here now? Okay, so this is the hypothesis function for logistic regression. Okay, and what happens that if you replace this, uh, and important thing is, as you can see, this is a two class problem. Okay, that is tumor or no tumor, and but there can be more class problems. Okay, in which there can be more than one class to classify. Okay, so in that case, we, as you can write this, as you can see, that multiplied numerator and denominator by e to the power this. Okay, so we get theta transpose plus theta 1 x. Okay, so uh, okay, so yeah, so you can see from videos here as well. Yes, yeah, so what he does here, like, so he has defined this theta 0 and theta 1 x as log of, okay, log of probability of happening by not happening. Okay, she did not get time to prepare the slides, that's the problem. Yeah, okay, so that is how we define it, and if you can uh, manipulate it, you'll get the same expression as this. Okay, and the important thing is that from this you can understand this, that the probability of happening, okay, is equal to, means if you can manipulate and you can find this px, you can see that this hypothesis equals to the probability of happening. Okay, if when our non-linearity here in the videos, the concept of non-linearity is not introduced. It is a hypothesis is equal to the probability of happening only when our non-linearity is sigmoid. Okay, as you can understand here, as I said, that what it means here is that when the hypothesis value gives 0.5, what this means that there is equal probability of it being a tumor, it being a cancer, and or not no cancer. Suppose here we get to zero point 0.7 here. Okay, so means there's 70% chance of having a cancer. Okay, and this is it. Okay, and and in the case of multi-class classification, we'll get to the expression more like this actually. Let me write it down. So that is it. Means like, as you can see, you can simplify it like this. Okay, and e e e theta 0 plus, so what is it like, let me explain. So this is a class beta, I think they, oh my god. So in this they have used the class beta, no, k class. Okay, yeah, so k class 1 plus summation of this. Okay, so so this is called this expression when we have this is probability of, as you can see, probability of x belonging to class k. Okay, so probability of it being k class given x value, okay, is equals to this. Okay, and this is and this function is called a it is called a, 1 minute, a softmax function. Okay, so softmax function is used for generating probability of in case of a multi-class classification, and we can use sigmoid in the two class problem. Okay, and another thing to explain here is there are various other non-linearity, like actually quite important to explain. Okay, so other non-linearity are ReLU, okay, and and tan hyperbolic, okay. So what happens is that, as you can see, you don't know gradient descent. I think should have explained that before. Uh, okay, so the idea is, um, yeah. So this is the sigmoid function. As I said, that we need to use this for gradient descent, and what happens is we need to differentiate the hypothesis in gradient descent. Okay, our this this first classifier did not work because more than x it is this, less than x is this. You cannot differentiate it. Okay, it's not possible to differentiate. Sigmoid is differentiable and nice. Okay, but you can understand that when the value of the this combination becomes large, okay, the value of the function does not change. Okay, so that is one problem of sigmoid. Okay, and okay, yeah. So so means so value of the function does not change. What does it mean? The derivative of this at higher values is always zero. Okay, so what happens that the means like it is called the vanishing gradient problem. Okay, that you cannot get to the means gradient descent will stop working at these values. Okay, so the other alternative of sigmoids are also there. As I said, ReLU here. So withdraw. Yeah. So ReLU is like this. Okay. So ReLU is like this. So for less than equal to 0, it gives it is 0, and for higher values it is like kx. Okay. So this is the ReLU. Okay. It is non-differentiable at 0, but that is okay. It is only 1 point. But at higher values, it always gives a positive value. Okay. Derivative is positive equal to k. But what happens is that for negative values, it gives derivative equals to 0. Okay. So the better alternative of ReLU is leaky ReLU. A very small derivative here. Okay. And in the negative direction. Okay. Like this. Okay. So it is called leaky ReLU. Okay. And tan hyper. Uh, any problem? Your mic is off. You're able to hear?
Yes, sir.
Means the presentation was off for some time. What happened? You were able to see as well? Somebody answer, please.
No, sir. No, sir.
Means the presentation was off, huh?
Yes.
So up to which part you have seen here? Multi-class done?
So, and now it's visible.
Multi-class classification you have
Yes, sir.
seen?
Yes.
Okay, okay. So
This ReLU and tan hyperbolic.
yeah. So as we are going in, so tan hyperbolic is very similar to sigmoid in shape. Okay. Uh, so this is sigmoid, okay, and tan hyperbolic is like this. So it is from -1 to 1 actually. Sigmoid from 0 to 1, and tan hyperbolic is -1 to 1. 1 actually, 0 not 0. Okay. So tan hyperbolic, you know, I think it is this function. Okay. In place of x, there will be uh, this uh, this linear combination. Okay. This linear combination. Okay. This tan hyperbolic is very popular. Means ReLU is more popular in neural networks. Okay, and tan hyperbolic is also used. Okay, but usually at the for last classification, means for the last layer, that it is this class or that class, sigmoid is almost always used. Okay, sigmoid, as you can see here. And if the multi-class problem is there, we need to use softmax function. Okay, like this. It is like compulsory for towards the last, means like when you are classifying this softmax and sigmoid is compulsory. You can use uh, okay, maybe not, I'll go deep into this. Okay, so up to this, any doubt? Up to this, any doubt?
No, sir. Sir, can you please go through some questions like week 3 and just related examples can you solve so that
Yes.
it will be beneficial actually?
Yes. So I will what are the problems? Let's see. So it is questions are nothing extraordinary. So question number 4, what will be the answer? Hmm? As you can see, we have this expression here. Okay, for the sigmoid. So you have to take anti-log both side. Okay, means raised to the power e, and then solve. Okay, you can do this. Question number 4 done. Hello, hello everyone.
Yes, sir. Sir, can you go through question number 5?
Question number 5. Let's see. Okay, so there are three class classification problem, as you can see. Okay, the condition of prior is there. Okay, I'll come to this. Okay, after some time. Okay, not now. This one is solvable, I think.
Sir, that question is a little tricky, so that I'm asking, like, actually, as it is mentioned, f of k is x, and the three classes are k equal to 1, 2, 3, where x in the input space, but in the option there is no answer like that. That's what asking. Can you just explain that question actually? Now, you don't tell the answer, but can you explain that question?
Uh, I will tell actually, but a little later actually. So I need to
Okay,
explain the
okay.
likelihood and prior of this one.
Okay, okay. No issues.
Question number three is solvable now. Okay. Uh, so as you can see this, okay. So question number three, what will be the answer? Okay, I have not explained this one as well properly. Let's see. Uh, uh, I will come back after a little bit of lunch break. Okay, 10 minutes. Okay. After that, I will explain. Okay. Question number three and question number five will be done today. Okay. Anything else will be done today? Yeah, basic logistic models with likelihood of Acha. Okay. That question number two will be done as well. Okay. 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 Question number one, I have not taught like that. Let's see. Question number six. Highest likelihood. Okay, okay, that will be done as well. Likelihood is very important to teach here. I'll do that. Just wait for 5 minutes, 10 minutes, and I will come back and cover likelihood and that which was this cost function of this one. Okay, thank you. Hello everyone. Okay.
Hello, sir.
Yes. So as we are finished with this, important thing is now likelihood. Okay. uh, so the likelihood here is defined as you have to understand it like likelihood is the distribution of the data, right, with respect to the parameters. And you can understand it like so let me explain. So the idea is here of, as you can see, the likelihood is always a distribution, right? uh, so we have gone into normal distribution mostly and Laplace little bit, and the now the thing is Bernoulli distribution means, okay, let's see. So the likelihood in case of this logistic regression is Bernoulli distribution, and let me explain why. Okay, so so the first of all the thing is like yes, so this is the expression actually. And and different from normal distribution uh, that you have seen, that was probability density function, but this is a probability mass function, which means that given this given this value, that is just to wait. Okay, so given this given this p and k, we are going to get the probability of the uh, of that of in our case that in that cancer case, okay, tumor. So probability that it is a cancer case or not. Okay, it is not going to give the probability distribution, but it is going to give the exact probability. Okay, so Bernoulli distribution is most popular actually. It is not hard to understand. Okay, so let me see where I can explain here. This is actually the coin toss example, not written here, I think maybe. So yeah, here written, yeah. So as you can see, so it is the coin toss example. So in our coin toss, what happens that the probability of falling head or tail is already known as half. Okay, but suppose it is not known, and a probability of getting head is p. Okay, and probability of not getting head, that is getting tail, is 1 minus p. Means it is a biased coin. Okay, and k represents whether head or tail. Head, suppose I represent by 0. No, head I represent by 1. Okay, and tail by 0. So up to this logistic regression you have understood, up to what I have taught today. First the L1 L2, and this introduction means intuition of logistic regression, sigmoid, and non-linearity, and this what it is called soft mass function. You understood up to this? Any doubt? Uh, yes, this is the one, right? Any doubt in this? No doubt, right? Hmm. So, as I was explaining, that k is 1 for head and k equals to 0 for tail. Okay, so you can understand that using this I can see that if suppose p is 0.2. Okay, so someone gives me like what is the probability of getting a head. Okay, so so this is 0.2 to the power k 1 0 point multiplied 0.8 to the power 1 minus k. Okay, and now the person tells me what is the probability of getting a head. So uh, as head and as he has said head. Okay, so k is equals to 1. Okay, so 0.2 to the power 1 and 0.8 to the power 0, so that is 0.2. So as you can understand, in our case also it is very similar. Here p in our case is the occurrence, probability of occurrence of tumor. Okay, and that k is whether we are looking for tumor or no tumor case. Okay, means cancer or no cancer case. Okay, so our likelihood here is this is the one. Yes, so likelihood here is and also you know that when the nonlinearity is sigmoid, the hypothesis and the probability is same. Okay, so h of x to the power to the power um, what's the convention here? Okay, so it is let me see actually what the convention.
The Unfortunately, it's not so.
Convention likelihood whatever. So it is the power of let me write it like this. Okay, uh, indicator function. Okay, okay, let me draw it. Okay, okay, so this is to the power of indicator function y value. Okay, and 1 minus h of x uh, h of x to the power y equal to 1. Okay, it's looking wrong. Oh, y equal to 1 and 1 multiplied 1 minus h of x to the power indicator function y equal to 0. Okay, you can understand this? Hello? You can understand this expression? Okay, so this is called the likelihood. Okay, as you can understand, probability of occurrence of 1, that is a hypothesis, and 1 minus hypothesis is the probability of not occurrence. Okay, and when, so you can understand, if we are looking for the probability of cancer. Okay, so as this is 0, so this is already 1. Okay, so only this part will be applicable. Okay, so that will be h of the x. Okay, and we, as you know, we need log likelihood. Okay, uh, as we need log likelihood, so log likelihood will become and so summation of uh, okay, another thing is, I mean, I've not written it rightly. This function becomes 1. Okay, okay, so this function becomes 1 and when y is equals to 1, and this I is the indicator function. Okay, which represents this type of function. Okay, 1 when y is equals to 1, and 0 when y is equals to 0. Okay, so no, here also it will be 1 when y is equals to 0. Okay, got it? So the log likelihood will become 1 when y is equals to 1. Okay, h of x, log of h of x, means you can do it, right? So this will be the likelihood, log likelihood, means that log h of x will come, this indicator will go in front. Okay, like that, and log plus log 1 minus h of x, and this indicator will come in front. Okay, so this is the idea. Okay, let's see if the problems are solvable now. Question number 4 is done. Okay, question number 3. Okay, so question number 3, it learns a model, which of the following are true about logistic regression. It learns a model for the probability distribution of data point in each class. Probability distribution of the data. So let's see. Yes, that is the true. Okay, distribution. This Bernoulli distribution is exactly that. Okay, distribution of the data in each class. Okay, yeah. Output of a linear model is transformed to range 0 1 by sigmoid function, right? Okay. Okay, parameters are learned by optimizing the mean squared loss. That is not correct. Loss function is optimized by using iterative numerical algorithm called gradient descent. Okay, gradient descent you have not studied. Okay, I'll tell it next time. Okay, but this is the answer. Okay. Now another is, yes, so this is the truth table given. Okay, acha, okay, probability the class label is 1. 4 input points. अच्छा, likelihood of observing data given these model parameters. अच्छा, okay, missed something I think here. Let's see. Uh, likelihood. Let me see. Okay, okay, yes, yes. So, as you can understand, this is actually summation over all training examples. Okay, summation over all training examples. Suppose I to M. Okay, like that you have to done. You have to do it. Okay, summation you have got here. Okay, that's a mistake here. Okay, as so this summation will be there. Okay, summation over I of training examples and this. Okay, so how will you solve this problem? Is like for y is equals to 1. Okay, so what will become? This will remain. Okay, so what will be like log of, oh sure, log is not required. Okay, so okay, so you can understand like h of x that is given 0.8 to the power 1. Okay, then then okay, this will be product actually. Yes, means after taking logarithm it becomes summation. Okay, okay, so product over 0.8 to the power 1 multiplied 0.4 to the power 1, 0.2 to the power, what will be here? 0.8 to the power 1. Okay, because it is 0. Okay, and 0.9 to the power 1. Okay, so that is the answer actually. Okay, this can be done. Question number 2, question number 3 done, question number 4 done, question number 5. Okay, okay, let's see. Consider Bayesian classifier for 3-class classification problem. The following tables for are given. Acha. Phi k denotes the prior probability for class K. Acha. For 3 classes, this at this points class condition density. Acha. Okay, so what happens in case of 3-class means multiple class problems, you can understand that it can be written like probability of one class, that is suppose k1, okay, to its power when it happens means like y is k1, okay, like that p of k2 to the power y of y k2, like that. Continue it till how many classes you have. Okay, so this is the multi-class for multi-class. Okay, this is product over all training examples. Okay, this is the likelihood for that. Now so prior probability is already given. Okay, probability of class K. Okay, so if all three classes have equal prior, means like there is no preference in them occurring, then it is all this likelihood case only. Okay, so which has the highest case of occurrence, which has the highest probability. Okay, so this is the 0.2, so class 2 will be the answer. Okay, rest I have not told you. Okay, so maybe we'll do it next time. Okay, and question number 6 can be done. Logistic regression model return results in the highest likelihood for this data. Okay, so this is also means not done exactly, but maybe you can do it yourself. As you can understand, there are these given. Okay, this is the hypothesis. Okay, and this is our likelihood. Okay, you can write the likelihood and maximize the likelihood. Okay, differentiating with respect to the parameters beta 0, beta 1, and beta 2. Using that, you will have three equations and three unknowns. Okay, you can solve it and get the value of beta 0, beta 1, and beta 2. Okay, no need to overcomplicate it. Okay, because logistic regression means in the videos it is given the closed form solution. No need to remember this. In logistic regression, almost always gradient descent is used. No closed form solution is ever used. Okay, so don't need to see the video, use the formula like that. Okay, just you have got this likelihood, differentiate it with respect to beta 0, beta 1, and beta 2. You'll get three equation and solve three variables and three equations, beta 0, beta 1, beta 2. Solve it and you'll get the answer. Okay, so uh, so doable. Hello, anybody? Hello, hello, are you able to hear me? So
Yes, sir.
yes,
Hello,
so
sir.
yes, so up to this it is done for today. Okay, any doubt to this? As you can understood, in question number 6, it is already just maximizing the likelihood, that is differentiating with three times, not three times, means with respect to beta 0, beta 1, beta 2, one time respect to each one. Okay, and prior part I have not told you. So question number 5, question number 4 is doable, 3 is doable, 2 is doable, 1 I have not explained it that way. Okay, these are doable. LDA, raster LDA, that I have not taught as well. Okay, guys, any doubt in this? Any doubt? No doubt, right? Clear. Okay, thank you very much, guys.